Hello everybody. I welcome all of you to the module 2 lecture 1, and the topic of our discussion today will be on ion exchange process. So the concept covered during this topic will be introduction to the ion exchange process. First of all, we'll talk about what is ion exchange, how this ion exchange process happens, then what are the materials which are involved during the ion exchange process? What type of material we use so that we can undergo the ion exchange reactions and ion exchange process, and the treatment of water or wastewater by using ion exchange materials. Similarly, we will also talk about what are the typical ion exchange reactions that happens when the ion exchange material comes in contact with the water or wastewater which contains the ions which we want to remove. And after that, we'll talk about the exchange capacity of the ion exchange resins, which is a very important term. The sense that if we want to design, if we want to find out that what amount of resins we require to remove a particular concentration of a certain ion present in the water or wastewater, then what should be the exchange capacity based on which we can decide about how much resin we require. And similarly, then lastly, we'll talk about the total ion exchange capacity versus the operating capacity of the resin. And in the end, we'll take a very small numerical which will tell you about how to calculate the exchange capacity. So the ion exchange process is a unit process in which the ions of a given species they are displaced from an insoluble exchange material by ions of different species in the solution. So here what happens that the material which we are having, that is the ion exchange material, or we also call it as resin. So this resin, it contains certain ions, and there are certain ions which are present in the water or wastewater which we want to remove. So the ions that are present in water or wastewater, they are exchanged by the ions which are present on the resins, which is again insoluble exchange material. And so it happens that the water or the wastewater is free from the targeted ions that we want to remove. For example, you can see here that the hard water coming here, so the hard water is made in contact with the resins which are present, or the ion exchange material which are present. So this ion exchange material contains sodium ions on it, and the all of you know that the hardness basically is caused by calcium and magnesium ions majorly, which are present in the water which you want to treat. So this is passed through this material, and we see that the ions, basically the calcium and magnesium ions, they are exchanged by the sodium ions, and the water which basically becomes free from these calcium and magnesium ions, and it is then basically laden with sodium ions though, but it becomes soft. So this is how the ion exchange process works. And this process is commonly used in various industrial and scientific, and as well as the water treatment and wastewater treatment applications. And the ion exchange material that we use is called the ion exchange resins, or it is also called ion exchange media. And they have an ability to selectively absorb the ions from the solution and release other ions in exchange, as you just now explained. So in the domestic wastewater softening, the sodium ions are replaced by calcium and magnesium ions, and thus it can reduce the hardness, as you have just now explained in this example is there. And ion exchange materials can be used for a number of water and wastewater treatment applications. For example, it can be used for the removal of nitrogen, it can be removed for the removal of heavy metals, it can be removed for the removal of total dissolved solid. So ion exchange process can be operated in batch mode as well as continuous mode. So batch processes are the processes where we want to treat the water which is coming out in a very small quantity, or the units or the industries where basically the generation of wastewater is small, or when we are applying this process in the laboratory scale, so then we generally go for a batch process. In the batch process, as you can see, that the resins basically they are put into a container, or we say it as a reactor. So in this reactor the resins are placed, and the solution that we want to treat is placed in this reactor, also known as batch reactor, and it is continuously stirred. So whatever the ions basically that we want to remove, so when they are removed or when the equilibrium is achieved or when the saturation of the resins takes place. So after that we stop the process and we filter out the resins or the media from the batch reactor, and we get the filtrate that we get is free from the targeted ions. So that is how the batch process works. And these materials which are coming out, that is the ion exchange resins or ion exchange media, so they are subsequently regenerated and they can be reused. And the industries where we are having continuous generation of the water or wastewater, so in that case we go for a continuous process where the exchange material is placed in a bed or a packed column, and the water which is treated is passed continuously through this column, right? In either it can be in the upflow mode or it can be in the downflow mode. The water which contains a certain targeted ions, so they are passed through this filter media, or basically which is packed with the resins, and the targeted ions, they are exchanged with the ions which are present on the resin, and then we can get the water, that is the effluent that is coming out, is free from the targeted ions. And as soon as the resin capacity is exhausted, then the operation is stopped and the column is backwashed, so that the suspended solids or the trapped solids which are there, they can be removed from the system, and then these resins which are there, so they are regenerated. So regeneration we'll talk in the coming lectures. So you can see here that the continuous process and the batch process for removal of the hard water. You can see that the ion exchange column is there and the water is being continuously fed into this column, and the ion exchange resins, so they may contain sodium ions on it here. So this sodium ions basically is exchanged by the calcium and magnesium ions, and the water becomes free from the hard water. Similarly, the hard water can be placed in a batch reactor, and this batch reactor basically can come in contact with the resins, and this can be continuously stirred, and when the equilibrium conditions happens, after that the water can be removed and we get the soft water out of it. That is an example of a continuous process and the batch process. So let us also talk about the ion exchange materials. For example, we can have the naturally occurring materials which can act as the ion exchange material, and similarly we can also have a synthetic ion exchange materials. Naturally occurring materials are mostly minerals which are also known as zeolites. So they are highly microporous crystalline aluminosilicate materials. The zeolite is having general formula of aluminate and silicate which is there, and here the M which is used here is mainly the H plus ions or the sodium ions. You can see here that the microporous structure of the zeolites, it helps in treatment of the water and exchange of the ions through these microporous structures. So it can be used for water softening, it can be used for ammonium ion removal, etc. Similarly, we can also have the synthetic ion exchange materials which are called resins, or they are also called phenolic polymers, and they are manufactured by using styrene and divinyl benzene. So they are copolymerides, so that we can get a tough structure which is insoluble structure, and that is known as resin. So styrene here serves as the basic matrix of the resin, and the divinyl benzene is used to cross-link the polymers so that we can produce a insoluble tough resin, which is mostly required because we want that the resin will be in contact with a solvent, or with, here we are talking of water, so it remains in contact with water continuously, so it should be tough or it should not be soluble inside the water, so that it can sustain the reactions that are taking place during the ion exchange. You can see here, this is an expanded view of the polystyrene bead. You can see here that we are having certain ions which are fixed to the polystyrene bead. So they are negatively charged SO3 minus ions. So they are there, and there are which are basically fixed in nature, and we are having the mobile positively charged exchangeable cations. For example, here in this case it is Na plus. So these ions can move, and these ions can be exchanged by the cations present in the water or the wastewater. And similarly, you can see here that the long chain compound, that is the polystyrene chain, is there, which acts as a base, right? And similarly, we can have the cross linking, which is done by divinyl benzene, which acts as a cross linking, and the shaded portion that you see here is representing the water of the hydration. Because as soon as these polystyrene bead, they will come in contact with water, they will swell depending upon, it will increase in volume depending upon the osmotic pressure that is developed inside the polystyrene bead. And this swelling behavior can be influenced by the chemical composition of the polystyrene bead. It will also be influenced by the structure, polymer structure, and degree of cross-linking plays a very important role here in the swelling of the polystyrene bead. And resins which have higher degree of cross-linking, they tend to exhibit lower swelling tendencies as compared to those which are having the lower cross-linking. So this may increase the toughness, this may increase the non-solubility, this may increase the lesser degradation of the resins in case when we are having high degree of cross-linking. But cross-linking can also have a certain disadvantage, that is if we have very high degree of cross-linking, then it may also restrict the ions movement through it, and this may also reduce efficiency. So we can have different type of resins which can be there, that is these are the synthetic resins which are made, and we can have different type of resins which are present. For example, we can have a strong acid cation exchange resins, and these strong acid cation exchange resins, so they behave in a similar manner as that of the strong acid, and they are highly ionized, and they are ionized at a different pH range. So we can use such type of resins for a long range of pH, and they are in the form of, for example, they can be in the acidic forms. For example, they can be R SO3H, sulfonic group is there, and similarly we can have in the salt form, that is R SO3Na also. So these two forms can be there for a strong acid cation exchange resins, and as the name suggests, so they are mainly used for the exchanging the cations which are present in the water or wastewater. Similarly, we can also have a weak acid cation exchange resins where the weak acid functional group, that is carboxylic acid group, is present, and they are weakly distributed. So this means that they can work in a very short range of pH, or generally in the acidic pH they will not work as they will not ionize. Similarly, we can have strong base anion exchange resin where the anions basically can be exchanged by the functional groups. For example, here we can have the OH minus as the functional group which are present, and they as a strong base resins, they are also highly ionized, and they can be used for a long pH range, and they can be represented by the general formula, that is NHR NH3OH. Similarly, we can have the weak base anion exchange resins where the weak functional group, for example, NH3Cl, will be used, and these are having a low degree of ionization, and again at alkaline pH it may not work, and that's why basically because it depends upon the degree of ionization where the ionization will not be possible, and that's why the use of such type of resins can be limited by the pH condition. And in the last, we can also have heavy metal selective chelating resins, which also behave like weak acid cation exchange resins, and they also have a very high degree of selectivity for the heavy metal cations. That's why they are called selective chelating resins. For example, we can have EDTA, ethylene diamine tetraacetic acid. You must be well versed, as you must have used it in during the experiment of total hardness, and the resin structure is in the form of REDTA-Na. So you can see here that the two structures, one is on the left hand side is the cation exchange resin. It is a strong cation exchange resin. Similarly, we can have strongly basic anion exchange resins. So here you can see that our SO3H group is there, where H plus basically is replaced by the cations which are present in the water or the wastewater. Similarly, you can see here that the strong anion exchange resin. So this is basically the OH minus group is present, which is mobile, and it can easily go into the solution or the water, and the anions which are present in the water, they can be exchanged by this OH minus. So the typical reactions that happens in the ion exchange, for example, we can talk about the natural zeolite. So it is represented by the formula Na2Z, and when it comes in contact with the water which is laden with calcium, magnesium, or ferrous here in this case, so they are replaced, that is the sodium ions are replaced by calcium, magnesium, and ferrous. So our formula for now this zeolite will become ZCaMg or Fe, and the sodium ions will go into the solution or the water. How the typical ion exchange reaction happens, and these reactions are always reversible reactions. And for the synthetic resins, we can have the strong acid cation exchange resin where RSO3H, that is the general formula, and when it comes in contact with the water which contains sodium ions, so sodium ions replace the H plus ions and H plus ions goes into the solution. And similarly, we can have this, now this resin can again comes in contact with the calcium ions which are present in the water. So calcium ions can replace sodium. So generally the divalent cations or divalent anions, they can replace monovalent cations or anions. So here calcium will replace sodium, and we see that the RSO3Ca becomes the general formula for this exchanged resin, and the sodium again goes into the solution. So that is how the chemistry of the strong acid cation exchange resin or any resin basically is there. For example, we can see that the strong base anion exchange resin. So here also we can see that OH minus ions can be replaced by chloride ions, and chloride ions will go on to the resins, and OH minus ions will go into the solution. Whereas when this type of resin, which has been exchanged by the chloride ions, so it comes in contact with the sulfate ions. So sulfate ions will replace the chloride ions, and sulfate ions will go into onto the resin, and the chloride ions will go into the solution. So similarly, the same reactions basically will happen for the weak acid cation exchange resins also, and similarly the similar reactions will also happen for weak base and exchange resins. Right. So the typical thing is that these reactions are reversible, and they basically they can have happen in both the ways, and these type of reactions basically generally happens when the equilibrium conditions are maintained. So we come to the properties of ion exchange resins. So the first and the foremost important property of the ion exchange resin is the exchange capacity. So the capacity of ion exchange can be expressed in the quantity of the ions that can be taken up by a specific volume of, right? Either it can be volume of the resin also, it can be the weight of the resin also, which can be either dry weight or it can be wet weight. So exchange capacity is always expressed in equivalents per liter or equivalents per kg or grams also, right? So it depends upon that is how many equivalents of the ions, targeted ions, they are replaced by the ions which are present on the resins, and per unit volume or per unit weight of the anion exchange or cation exchange resins. So this is how the exchange capacity is defined, and this exchange capacity will be very beneficial when we calculate that how much amount of the cations or anions have been replaced, and similarly it can also tell us about what should be the amount of resins that needs to be placed if you want to do in particular amount of cations or anions in the solution. Similarly, a very important property is the particle size, which affects the hydraulics as well as the kinetics of the ion exchange. For example, if we are having a column and in which we are packing the resins, as the size will lower down, the hydraulics of the ion exchange column will be impacted, as the lower the size, the lower is the movement of the water through this ion exchange column. And if the ion exchange column becomes highly packed, then it becomes very difficult for the water to move through it, and that basically becomes a constraint. Similarly, the kinetics of the ion exchange will is dependent upon the size, and as the size reduces, the kinetics increases. Right. So as the rate of exchange is inversely proportional to the 1 by d square, that is the diameter of the resin particle. So that's why as the size decreases, the kinetics of the ion exchange increases, whereas the hydraulics of the ion exchange is adversely impacted. Then the last property is the stability, which again is very important factor. For example, when we are putting this ion exchange in contact with water or wastewater, so the stability plays a very important role, because the ion exchange may shrink or it may swell depending upon the osmotic pressure that is developed inside the resins, and it may also basically cause degradation of the resin if we are not having very high degree of the cross-linking. Similarly, these properties also become important when we are storing ion exchange resins. Then these properties also become very of utmost importance. So the ion exchange capacity of the resins, we can have two types of, we can divide it into two parts, that is the total exchange capacity and the operating exchange capacity. Talk about the operating exchange capacity later on. First of all, let us talk about the total exchange capacity. It is defined as the total ions exchanged per unit mass or volume of the resin. So this means that whatever the number of ions which we want to remove from the water or the solution, so the equivalents of ions, or basically the number of ions that are exchanged per unit mass or per unit volume of the resin, so this is known as the total exchange capacity. Till the resins that we are using, that is basically we are using cation exchange resin or the anion exchange resin, so they become exhausted. That is the initial concentration which is being put into the ion, in the contact with the ion exchange resin. So this becomes equal to the effluent concentration. So this means that our ion exchange have totally exhausted, and then we can define that whatever the number of ions that have been exchanged till then, so this represents the total exchange capacity of the ion exchange resin. So it can be again expressed in milliequivalents per liter or equivalents per liter or milliequivalents per grams or milliequivalents per kg or equivalents per kg, whatever. So these units can be used for defining, for representing the total exchange capacity of the ion exchange. For example, we can see here the synthetic resins, they are having a capacity of around 2 to 10 equivalents per kg, whereas zeolites, they may be having a low capacity, that is around 0.05 to zero point 0.1 equivalents per kg. Now, how to measure the exchange capacity, the total exchange capacity of the ion exchange resin? So it depends upon by placing the resins in a known chemical state. For example, when we are having a cation exchange resin, so it will be first washed either with a strong acid or with a strong brine solution, so that whatever the sites which are there on the ion exchange resin, so they are totally exchanged by H plus ions or they are totally exchanged by sodium ions. After doing this thing, then we basically take a water or wastewater which contains a known concentration of the exchangeable ion. For example, let us say we are having a solution which contains a lot of calcium ions. So we should know that what is the initial concentration of the calcium ions which is there, and this is introduced into the resin column, and the calcium ions, they basically replace the sodium ions or the H plus ions which are present on the resin, and then we measure, that is how much after the operation is stopped, that is basically when the resins becomes exhausted, that is all the sites are exchanged by calcium ions. So this means that the concentration of calcium which is being put onto the column is equal to the effluent concentration. So at that point of time, we stop the operation and we measure that how many total equivalents of calcium ions were exchanged by the unit weight or unit volume of the resins. So this tells us about the total exchange capacity of the resins. Now, exchangeable capacity can also be defined in terms of gram calcium carbonate per cubic meter of resin. That is, 1 equivalents per cubic meter is equal to the 50 grams of calcium carbonate per cubic meter. That is, we know that equivalent weight of the calcium carbonate is 50 grams. So the 1 equivalents per cubic meter may also be represented as 50 grams of calcium carbonate per cubic. In contrast to the total capacity, operating capacity is measured by the useful performance are obtained with the ion exchange material, that is, which depends upon the prescribed set of conditions. For example, suppose we want to remove from water or wastewater a certain amount of cations or anions, or we are having a certain limits, a prescribed limit, that is, it should not exceed in the water or wastewater, the effluent, the concentration of certain cations or anions should not exceed in the wastewater uh, beyond a permissible limit. So that defines the operating capacity now. Okay. So this means that though the resin may not have reached its total capacity, but because the concentration of the targeted cations or anions have exceeded a certain limit, so that we have to stop the operation, and that defines the operating capacity of that resin for that particular type of ion. So it will depend upon a number of factors. For example, it will depend upon the total capacity of the resins. It will depend upon the level of the regeneration that is being done to the resins. It will also depend upon the composition of the solution that is to be treated, how many type of ions basically it contains, or what is the ionic strength of that water or wastewater basically being treated. Similarly, the flow rates through the column will also define the operating capacity. That is, higher the flow rates, the operating capacity reduces. Similarly, the temperature basically affects the kinetics of the reaction, so also define the operating capacity. The particle size and distribution we have already discussed in the right? So that also defines the operating capacity. And similarly, the selectivity of a certain type of cations or anions that we want to remove, so that also defines about the operating capacity. In general, if we represent the operating capacity by X, so this may be equal to the number of equivalents of ions of interest which is applied to the column divided by the resin volume minus the number of equivalents of ions of interest passing through the column divided by the resin volume. So this gives us the operating capacity up to the point at which we stop our. We'll discuss this in the coming examples. So this curve you can see here that it basically represents a very good example for the total exchange capacity and the operating capacity of the resin. For example, you can see here that on the y-axis we are having the residual hardness expressed in ppm. We can also express it in terms of equivalents per liter also, and on the x-axis we are having the volume which is passing per unit volume of the resin. It can be volume per unit weight of the resin also. So we can see that as the total hardness here is A to B, so it represents the total hardness which is present in the feed water. So the total hardness that is basically subjected to the resins. So we can see here that as we feed the water which contains total hardness of A to B, so this hardness slowly and slowly reduces as then the hardness causing cations. So they are exchanged by the sites which are present on the resin, and slowly it reduces. It goes down below a point which sets our quality limits. So you can see here that suppose we have put a certain quality limit that the product water should not contain a certain amount of hardness. So this sets up the quality limits, and this sets up the point, this point F, which defines that now our hardness is going below the hardness that we require the effluent. So it may go down further as because the sites are present there and they are exchanging continuously cations of interest. So then slowly and slowly the sites basically they get exhausted, that site gets started getting saturated, and then the concentration in the effluent it starts increasing, and you can see here that at point C it crosses our quality limits, right? So if we continue our operation, then so we will see that continuously our concentration of the cations of interest they will rise, and they will reach to a point G where we are having the concentration same as the feed concentration. So this means that our key point here is called the break point where we have exceeded our quality limits, and the point G represents the exhaustion point where the quality where the total capacity is now exhausted, or the whatever the resins are present, so they have exhausted at this point, and that's why it is called the exhaustion point. And the yellow area which represents above the red line, it represents the total capacity. For example, this area here that I am basically shading, or the yellow area, so it represents the total capacity of the ion exchange resin. And similarly, if we see if the operating capacity, so in that case, the area which is lying above the TDEF region, that is basically wherever we are having the concentration of the hardness lower than what is required, what is prescribed by the quality limits. So this area will give you the operating capacity of the, right? I think the difference between the operating capacity versus the total capacity must be clear to all of you, and the total exchange capacity will remain same because it represents the all the exchangeable sites which are present on the resin, whereas the operating capacity of the resin will be very specific to the test conditions. It will depend upon the conditions which are laid down for the quality limits. So let us take an example, that is we are having 1000 liter of water which needs to be softened by ion exchange method. For the regeneration we are using 150 liters of zero point 0.1 normal of HCl as well as NaOH for the anion exchange as well as the cation exchange resins. So we need to calculate the hardness of the water of the sample. So as we know that the amount of acid or alkali that is being used to regenerate the resin, so this is equal to the hardness of the water sample. Whatever the amount of acid or alkali that we have used, so that we can regenerate either the anion exchange resin or the cation exchange resin. So this will represent our total hardness of the sample. So in this case, we are using around 150 liters of zero point 0.1 normal of HCl or zero point 0.1 normal of NaOH, right? So this means that around 15 liters, if we say that if 15 liters of 1 normal of CaCO3 in this case, because we want to express it in terms of calcium carbonate. So around 15 liters of 1 normal calcium carbonate we are using for regeneration purpose. And the 15 liters or 1 liters of 1 normal calcium carbonate represents 50 grams of calcium carbonate. Yes. So 15 liters of 1 normal calcium carbonate will represent around 750 grams of calcium carbonate. So this means that for 1000 liter of water, we require around 750 gram of calcium carbonate in terms of equivalents we are talking about. So this means that around 1 liter of water will require around 0.75 grams of calcium carbonate equivalents. So the hardness of the water can be represented as 750 milligrams per liter, as we can convert this 0.75 into milligrams, and then this will represent, that is around 750 milligrams per liter of calcium carbonate, as calcium carbonate basically is required, and that represents the hardness of the water. So we stop here and we'll talk about the ion exchange chemistry in our coming. Thank you.